Hi.
We're present. Sorry.
Welcome to Math 119-312, the mathematics of pandemics. Today we're going to be talking about simple mathematical models, I'm assuming for things related to COVID and diseases.
Yes.
Okay, so when we go about building a basic model for infectious disease outbreaks, the first thing that we can do is kind of look at the data of outbreaks and see whether the data has some sort of characteristic shape. So if we look at some data that we have here, the first image that you see is from a salmonella outbreak in the US in 2018. So you can sort of see that it starts off with some sort of exponential growth, and then there's like a plateau at the top, and then the cases start to decrease. And you can also see that with the COVID-19 outbreak in China on the bottom left, there's some sort of exponential growth, and then there's like an anomaly close to the top, and I believe that was because they decided to change what counted as a COVID-19 case halfway through the pandemic in China. So that was sort of why the anomaly is there. And then there's a plateau at the top, and then the cases start to decrease again. And then on the bottom right, we see data from the SARS outbreak worldwide. And again, this is slightly different because there's lots and lots of waves of outbreaks. But again, in each wave, you sort of see a similar shape. There's some sort of exponential growth, a plateau, and then decrease in cases again. And then the waves just continue for that one. So if we go about building the most simple model possible, we can sort of consider this scenario here. So if we consider an infectious disease outbreak where each infected individual infects two other individuals. So we're starting with one person who infects two people, move to 4, then to 8. So we're sort of getting this geometric progression, right? So if we plot the graph, it's going to look like what it looks like on the right there. And now what's wrong with this model? So essentially, people are just being infected infinitely. There's no sort of limit on the number of infections, which we know is not realistic because the disease will eventually run out of people to infect. So this is where we come onto the idea of something called compartmental modeling. Now, compartmental modeling will essentially split the population into different compartments. So if we go about building the most simple compartmental model, we can use a susceptible category and an infected category. And the rate at which people move from the susceptible to infected category is this beta SI term. Now, this beta SI term, it essentially just, so it gives rise to these two differential equations over here. So this ds by dt term, which is the rate at which people are moving from the susceptible category, and di by dt term, which is the rate at which people are moving into the infected category. Now you can see that the rate of change of the susceptible group will be negative because as the disease progresses, there will be less people in that category, and vice versa for the infected group. So yeah, so if we model this SI model, then we'll get a graph that sort of looks like the one on screen right now. So we've sort of fixed the problem of infecting an infinite population. However, once the population, the entire population gets infected, they're remaining infected. So to fix this, we can just add a new category to our population. So an R category. So over there it says it indicates the recovered population, but we can also think of it as it indicating the removed population. So that will include both the recovered and people who have died from the disease. So next slide. So this is what our new model will now look like. So we have this new term, this mu I term, which goes from the infected category to the recovered category. So this mu I term is basically the rate of change of the recovered uh, category. And we can see that the second equation there has also changed to capture both the movement from the S to the I and the I to the R category. So if we model this, now we get something which looks much, much more similar to the characteristic curves that we saw in the first slide. We have this sort of exponential growth at the beginning, and then we have this plateau at the top, and then the cases start to decrease. And this is called the SIR model, or the SIR model. And it is a pretty accurate model, given that we only implement two parameters. It can capture the shape of infectious disease outbreaks in a very simple way. Now, Clayton, if you just go back to the very first slide. Yeah, so as you can see, like real life data doesn't actually look like the smooth curve that we had in our SIR model. There's sort of this like jaggedness in the graphs. So if you go back to the last slide, so that's because infectious diseases are inherently random. There's this sort of random nature to the outbreaks. Now, to capture this randomness, we can use something called stochastic modeling. So we can make a stochastic SIR model. So instead of this smooth curve, how we can think about it is we're essentially flipping the coin lots and lots of times. And this coin is weighted on, so the coin flip will essentially determine whether someone moved from the S to the I category or the I to the R category. And it's not just a 50-50 coin, but it's going to be weighted depending on how many people are in each category. So for example, if there's lots of people in the susceptible category, our probability of a infection next flip will be very high. So this stochastic modeling can give rise to lots and lots of different curves. So in one model, we can have a very high peak and then decreasing, or we can have a small peak and then the numbers start to decrease. So this stochastic model is sort of a basic extension to the SIR model on how we can make, and it helps us make the model more realistic. So yeah, now I'm going to pass on to Alex, who's going to talk about some parameters that we consider when we're making these models.
So when we want to make a model modeling COVID-19 specifically, there are a few main things that we want to think about that will determine sort of when we want to determine the parameters of the SIR model, beta and mu, and then also out of the removed population, what percentage of people are dying. And so that would be one would be the effective reproductive number, RT, which is essentially the number of the number of people each person who is infected then goes on to infect, and that's proportional to beta in the SIR model. And then we also want to look at the fatality rate because that will determine of the people moved from the infected to the removed category, what proportion of these people will die versus recover from the disease. And then we also want to look at the length of infection because that determines mu, so who is how many people are being moved from the infected to the recovered category in a certain cycle. So as a lot of other groups have talked about, the reproductive number, R0 is the basic reproductive number, which is the average number of people an infected person will infect without any sort of public health measures initiated or put in place. And so for COVID-19, this is likely around 2.5, but estimates range from 1.4 to 4. And R0 is partly inherent to the disease biologically in terms of the way in which it spreads. However, it does depend on location because it does depend on sort of how often people are, how densely populated an area would be, or how often people tend to interact with each other. And then so if we want to get a look at the what's actually a more accurate, or if we want to look at a more accurate number that to determine the spread of the disease, we can look at RT, which is the effective reproductive number, and that's the infection rate with public health measures initiated, and that of course is influenced by many factors. So we can look at the RT for Massachusetts through the pandemic, and you can see it starts out in March around 2.3, and then as these public health measures are initiated, it drops down to below 1 for a while, and then you can see it's slowly been creeping up to around 1.18 as of a few days ago. And so for R naught and RT, if it's above 1, that was what would lead to the exponential spread of the disease, and below 1 will lead it to lead it to be lead it to eventually come under control. And so one big thing in COVID, in terms of COVID, that influences RT is, and R naught, is the, or at least how we report R naught and RT, is the number of undocumented cases, since 40% of all cases are asymptomatic according to the CDC. And then in addition to those asymptomatic cases, there are mild cases that may not be reported because a person doesn't go and get a test. And so these cases need to be accounted for when we're determining what RT is. And although they need to be accounted for, they're generally less infectious than confirmed cases. So according to the CDC, asymptomatic cases are around 75% as infectious as confirmed cases that are symptomatic. And so if we look at these graphs on the bottom of the slide, this is a study of Wuhan, which it showed that so this study determined that asymptomatic cases or unreported cases are around half as infectious as reported cases. So that's where the mu equals 0.55 comes from, and you can see that when you account for these cases, when you have you can see the daily cases are a lot higher over time than if you assign mu to be 0, which is just if those cases don't matter and don't factor in to the spread of the disease. So we can see that is a big thing we want to think about when looking at RT and making our model.
There are some microphone issues. I'm going to just mute everybody, and then when you're speaking, unmute yourself.
And so in addition to thinking about undocumented cases, of course, factors influencing RT include non-pharmaceutical inventions. So if you want to look at broadly, look at social distancing, and that would just be reducing each person's number of contacts. And this study looks at how the impact of no social distancing, mild social distancing, and strong social distancing on the spread of COVID. And so mild social distancing would just be like limiting some closures and limiting interaction with other people, and strong social distancing would be sort of a lockdown type scenario. And so in figure A, you can see the spreading, how the rate of spread of COVID changes, and the dotted line would be equivalent to an R of 1. And so you can see with no social distancing, it remains quite high. With mild social distancing, it lowers slightly, but still remains above 1. And with strong social distancing, you can see it dips below 1, and that then translates to, in the graph on the right, in green is the only curve that comes under control. And so another factor that influences RT, of course, is masking. And one study found that an increase in mask wearing is associated with increased odds of transmission control, and that would be defined as getting RT below 1. And then another study found that mask wearing can decrease RT even if masks are as little as 50% effective. And that's what we'll see on the next slide, with this chart showing what the effective reproductive number can be with different proportions of the population wearing masks and different effectiveness of masks. And that this is split up into, if we think that R naught for COVID is 2.2 versus 4.0, and you can see that even if say oh, and then it also shows whether wearing the difference between wearing the mask all the time and wearing it only just post symptoms. And you can see that even if the masks are only 50% effective, if 100% of the population are wearing them all the time, you can see our RT gets down to around 1 and can help to slow the spread of the virus. And if the masks are even more effective, then you can get it below 1 and essentially bring the pandemic under control. And so this is just looking at some other non-pharmaceutical interventions and how they impact RT, and this divides it into whether this is the first intervention that's put into place by a community versus a later intervention. And so you can see that a lockdown can reduce RT by around 50%. And then these other measures, including banning public events, closing schools, self-isolating when exposed, and social distancing in general can reduce RT from around 10 to 25%. And so that those factors that influence RT are generally what is influencing people moving from the susceptible to the infected category and how fast that occurs. And so now we can look at for people who are moving from the infected to the recovered category, what percentage of these people are recovered versus dying. And so that's of course the fatality rate of COVID. And this also is influenced by the undocumented cases that I talked about earlier, because if you look at case fatality rate, which is just the total number of deaths over the total number of reported cases, that is around 2.2% in the US. But since there's a large number of cases that are not counted, it's better to look at infection fatality rate, which has to be estimated because we don't know the exact number of infected people. And so estimates range from 0 to 1.54% of all cases, and the median is 0.27%. And this varies a lot based on age demographics, according to the CDC. So 0 to 19 years, there's around 0.003% infection fatality rate. From 20 to 49 years, there's around a 0.02% infection fatality rate. 50 to 69 years, there's around a 0.5% infection fatality rate. And for 70 and up, it's around 5.4%. And so this can be helpful if we want to later modify our SIR model to separate it into categories. And then the last main thing we want to think about when determining the sort of model coefficients beta and mu is the length of infection, because that determines mu, how fast people are moving from the infected to the removed category. And so for COVID, the average incubation period is around 4 to 5 days. and then and then that's basically to the start of symptoms. For mild to moderate cases, according to the CDC, they're infectious for around 10 days. 10 days after the onset of symptoms is when they're no longer infectious, and that's also the length of required isolation for asymptomatic cases, which would imply that that is also asymptomatic cases also are no longer infectious after around 10 days. And then that can be higher for severe cases, but it's likely no longer than 20 days. 88%, it was found that 88% are no longer shedding replication competent virus after 10 days of these severe cases, and 95% are no longer shedding this replication competent virus after 15 days. And that replication competent virus is just virus that will then infect other people and cause disease. And so these are just the three main points we want to think about when determining our coefficients for our SIR model in terms of COVID itself. Next slide. Or now Clayton is going to talk about more specific SIR model things.
Yeah, so that's where we get the coefficients to run the model. I'm going to talk about how we actually can implement this SIR model. So the simplest way mathematically is just the matrix SIR model. So we did this in some homeworks, but you look at the population at time t as a vector, st, it, rt, and then you have some fixed matrix A, and at every step in time you multiply your vector by that matrix A. And so an example is just something like this. This is a simple A matrix. And remember, you can also write this as a system of linear equations. So that's how matrix multiplication works. You're just going to get these recursive relations for each one of these. So there's issues with this though, which is, for example, in our last model that I just put up, the total population remains constant, but the susceptible population will become negative by time 14. So that's not good. You can adjust parameters to avoid negative populations, but this will give you just a simple exponential curve and you'll lose that characteristic shape that we wanted to see. So it won't be a realistic model. So the next step is to change this by adding these cross terms to make it no longer be a linear recursive model. So now we'll always have non-negative populations, and it's going to be more realistic. We're going to get a better shape, and it's going to be a more accurate model over time. So that's the nonlinear SIR model, which is the SIR model, but with the cross terms. So the advantages, like I talked about, it's better, it looks better, and you won't get negative populations ever. The disadvantages are that you cannot give closed form expressions to solve it. So if you want to find what are the numbers at time t equals 100, you have to calculate the first 99 to recursively get the 100th. You can't just plug in 100 into some closed form expression. The next way you can do a SIR model is the differential SIR model, in which you use a system of differential equations. This is probably the most common one, so this is the classic example, is ds dt has these beta and mu coefficients, which we can find as she just talked about. So this is the most realistic, and time is continuous as opposed to in discrete steps like in the other models, which is better. The problem is it can be more difficult to explain and to understand, and it cannot be explicitly solved at all. So we can only estimate its value at a given time. So I'm going to talk about how we do that. So Euler's method is probably the most common way that mathematicians model differential equations that can't be solved. So what you do in Euler's method is you treat each step as if it was linear. So if this is the susceptible population over time, and we have the populations at time t1, then slope and take a small step as if it was linear. And then we'll do that repeatedly with very small steps to get as accurate a representation as we can of this equation. And then Runge-Kutta is a more accurate tool for estimating differential equations. Euler's method is actually equivalent to first order Runge-Kutta. The classic Runge-Kutta is fourth order, but it gets very complicated very quickly. So these would be the quantities you would need to calculate to do one step of a classic Runge-Kutta for a SIR model. So as you can see, the equations get really ugly really fast. So this is a big disadvantage because, as we've talked about earlier in the course, a model is only worth what you can convince people that it's worth. So it might be harder to sell this model to someone and convince them it's realistic. For our approach, we decided to use the nonlinear system of equations, and we noted that Euler's method is effectively the same as recursively calculating with the nonlinear model if you take sufficiently small step size, if your time intervals are small on the recursive. So now I'm going to talk about a few extensions on the classic SIR model, so that's susceptible, infectious, removed. So one is the SIS model, which stands for susceptible, infectious, susceptible. This is when this happens when the same person can contract the disease multiple times. So persons who would be removed are instead just returned to susceptible. This isn't super good for COVID-19 because reinfections, while they do exist, evidence suggests they're very uncommon. And this doesn't have the removed category, so it's harder to track how many people have died in your model, which is really the most important thing that we're looking for. So we decided not to use SIS. SEIR model is another common extension. So it introduces the exposed compartment, which is people who are in the incubation period. So someone who's been exposed will become infected and infectious, but for the time is generally just, they will get it soon. So this, again, isn't very good for SARS-CoV-2 because one of the reasons it's so contagious is because it is infectious during the incubation period. It is infectious before it's symptomatic. So the exposed category, as it's usually used, is not applicable to this virus. So we didn't use this one either. And these two models are often used in conjunction. So you might use like an SEIS model if you want to send people, have the exposed and send back to susceptible. Another common extension is SIRD, so susceptible, infectious, recovered, deceased. So it easily allows how to track. So remember, R is usually removed, but here we're going to look at R as recovered and D as deceased and separate those out to get a fourth component. So this is helpful because it can show the value of flattening the curve because you can concretely say, look, less people die if this happens versus this. However, deaths can just be calculated later as a proportion of removed. So we thought it was not helpful enough to add another compartment when we could just multiply by the fatality rate at the ends to get an approximation. Now I'm going to turn it over to Max to talk about our model specifically.
Okay, so we've talked a lot about specific or about general COVID models and what we might keep in mind when making these models. But now we're going to talk about the specific model that our group created. So we actually created two models here. This is this model right here is the SIR model effectively, but it uses multiple compartments for both the S and the I groups. So as you can see here, we have the S sub U group and we have the S sub E group. And the S sub U group refers to uneducated, susceptible individuals. And basically what this means is individuals who aren't going to be following social distancing practices and mask wearing. And then we also have the S sub E group, which we call educated. And these people are going to be following social distancing and mask wearing. And the reason why we decided to split it into these two groups is basically because we believe that that those who are educated will have a significantly smaller infection rate than those who are uneducated. So if you look at the first equation, this equation is basically just the SIR model, but there's also an extra term here, which is the J times S sub U n term. And this term actually removes people from the S sub U group and places them into the S sub E group. And the reason why is because we're modeling education as an exponential factor. So basically, I think in our model we used 0.05% of people at every time step are going to become educated. And yeah, this is necessary in order to ensure that people become educated at all, because at the start of the model, we assume that everybody is uneducated. And then we have both the I and the R terms are the same as the regular SIR model. And then if you sum all these equations together, you'll find that this will just equal N, which is the total population. And then we start our initial parameters with N minus 1 people in the uneducated susceptible group, and then 1 person in the uneducated infected group. Okay, so here this model has 4 parameters: K sub U, K sub E, J, and M. And so we also represent the movement from the nth stage to the n plus first stage as one time period. So in our specific model, this time period refers to a day. And then K sub U is going to represent the quantity of people that an uneducated, infected individual interacts with, times the probability that a susceptible individual who interacts with this person gets sick. So basically, this is really related to the beta parameter in the SIR model. And it's also related to the R naught value. So the number of people that each infected individual is going to get sick. And then K sub E is going to be pretty much the same thing, but for the educated infected individuals. And then this is going to be closer to the RT value. So the amount of people that someone who follows social distancing practices will get sick. Okay, so now I'm going to show the Excel demonstration of the model. So there's a lot here to look at, but I think the most important things are these 4 parameters. So as you can see, we have the K sub U, the K sub E, and the M and the J parameters. And so these parameters correspond to a time period of 1 day, as you can see here. And they also correspond to approximately 3.5 people infected for each uneducated infected individual, and 0.7 people infected for each educated individual. And then you can see the results of this model in the selected graph. So as you can see here, under these parameters, the recovered group is going to flatten out, or sorry, the removed group is going to flatten out around day 217-ish. And this basically is when herd immunity happens. So when enough people have been placed into the removed population for the virus to be unable to spread. And something crucial that you can see is that this model is somewhat volatile with respect to the parameters. So if we were to change the K sub U parameter to 0.2, you can see that the recovered group moves down significantly. Sorry, the removed group moves down significantly. So the results of the curves are substantially different depending on what we have for these parameters, as you can see. And again, these parameters can't really be determined to very great accuracy. So that's one flaw. And then the model is also relatively volatile with respect to the J parameter. So how many people are moved from the uneducated to the educated group. So if we increase this by only a small amount, you can see that the removed population is going to reach herd immunity at a significantly smaller quantity of people infected. Okay, so yeah, this model has a fair amount of limitations, as with any math model. So it doesn't really allow for the handling of multiple NPIs or non-pharmaceutical interventions. So even though we were able to model mask wearing and social distancing, it can't really handle stuff like state mandates. And then this model also doesn't separate separate the treatment of individuals by age. And we know that COVID does affect individuals of a certain age very differently. So that's something that this model can't do. And then also, as I said before, the parameters cannot be determined to sufficiently great accuracy. As you can see, the model is volatile with respect to the parameters. And then the model also doesn't account for any location factors. So it can't assess the spread of the virus to particular locations within the USA. And it also doesn't admit a closed form. And so we have certain assumptions as well. So we assume that educated individuals are equally likely to be infected from the virus as uneducated individuals. And this basically refers to the idea that mask wearing is only going to be effective if the person who's wearing the mask is infected and the person who isn't wearing the mask is uninfected. So basically, it assumes that wearing a mask when you're uninfected will not prevent you from becoming infected if there is an individual who's not wearing a mask and is infected. And then it also assumes that educated infected individuals are less likely to spread the virus than uneducated infected individuals. So basically the idea that what we know about social distancing and mask wearing is actually true. And then it assumes that the USA is a closed and localized system. So there's going to be no people from other countries moving to the USA, which also means that the population within the USA is static. And then also the location within the USA is going to have no impact. So it basically, if somebody's from a different town, then they're going to be equally likely to be infected, which is an unrealistic assumption. And also our only artificial inhibitor to the spread of the virus is going to be education. And as we said before, we assume that age does not affect the spread of the virus. Okay, so that was the two-group model, which is the more simple of the model that we created. But it's also desirable to create a model that accounts for more population groups split by age, because as we said before, age can have a relatively major impact on the way COVID spreads. So in order to describe this more general model, we're going to have to use linear algebra. So if we suppose that the population is going to be split into p distinct groups, so that we have p susceptible groups, p infected groups, and then p removed groups, we can then create a matrix of interaction coefficients, which actually should be p by p and not m by m. And then this is going to represent the number of people belonging to a group that a person from another group may infect. And this is how that matrix looks. And now we can define a new matrix, x sub n, to be a p by p diagonal matrix, whose diagonal elements are the susceptible population. And now we denote a vector, s sub n, to be the n-dimensional vector with basically all the p groups of the, all the p susceptible groups. And then we can define I sub n and r sub n to be similar. And now using all of these defined values, our model can basically just follow the exact structure of the SIR model, which is a pretty, it's a pretty nice way to split the population into different groups and still get a model that looks exactly like the simple one. And so here, the M parameter is going to represent the frequency of recovery of the virus. So basically the same as the two-group model. And then the N parameter is going to be the total population. And so As with the two-group model, we note that if these P groups are split into uneducated and educated groups, then we can add an additional education term to the first equation. And then this is going to remove people from the uneducated susceptible groups and move them into the educated susceptible group. And so this model is going to have these interaction coefficient parameters, which determine the rate at which people will spread the virus. And then the M parameter, again, is going to be the same as the two-group model. Okay, so now I'm going to show the Excel sheet for the general model. Okay, and so there's even more to see here, but basically we have these, this is the interaction coefficient matrix. So as you can see, we split the groups into U1, U2, U3, and U4, as well as E1, E2, E3, and E4. And so basically, these represent the age of the individual. So the U1 group is going to be age 0 to 19. The U2 group is going to be 20 to 49. U3 is going to be 50 to 69. And U4 is going to be 70 plus. And then the E groups are the same thing, but they're just the educated versions of those age groups. And so the most important thing that we can look at with this model is the death rate, because as we know, the death rate is different depending on age. So we have the death rate parameters here, and these are taken from the CDC. They just referred, I think Alex has referred to them in the past. And so this is what the death rates are for each group. And we assume that the educated individuals are going to have the same death rate as the corresponding uneducated individuals. And so we can look at the effects of these varying death rates on the total deaths. So these 8 columns represent the total deaths throughout the virus. And so if we scroll down to the end of the virus, then we can see that this quantity, which is the U4 group, is going to have the most, it's going to be the greatest value out of the other three groups. So we have 1.3 million deaths in this group, whereas for the U3 group, we only have 101,000, and it gets smaller from there. And then for the educated groups, we're going to see larger parameters, and this is because more people are going to move into the educated susceptible groups than those who started with the uneducated susceptible groups. And so these, the fact that there are more deaths within the higher groups is what we should expect from this model, and it also more closely models how COVID acts in real life. Okay, so the reason for making a model more complex is so that you can account for more factors. So this model can account for the drastically varying effects of COVID based on age. And it can also predict the COVID effects in a partially vaccinated population by creating a new population which is rarely infected. So pretty much the fact that we have the ability to create, more than 2 different populations means that we can study the effects of more factors that can cause varying infection rates. And then it can also predict certain NPIs other than education, again, by creating a new population. And it achieves more generality while still maintaining the, the simple structure of the original SIR model. And so the problems with this approach is that the quantity of different parameters that we have is p squared plus 2, which is quadratic in the number of population groups. So basically, the more population groups we add, the more parameters we need to keep track of. And so uncertainty in any of these parameters is going to affect the final shape of the model. And even though we can still assume certain things about the k parameters, which can then reduce the different quantity of parameters that we have to keep track of, but this results in having certain assumptions. And so, yeah, these interaction coefficients are practically infeasible to calculate. So because of that, the model will likely have limited application to reality. And still, the model cannot account for location effects. And so this model, again, assumes that the USA is a closed and localized system and that location has no impact. And then there are also no societal effects that exist temporarily across multiple populations. So for example, if a legal mandate happens after day 100, our model can't account for that because it only accounts for like a continuous movement of individuals into different populations. And then also the interaction coefficients between any two populations will remain constant over the lifetime of the virus. So as Kemal was talking about, some SIR models use stochastic coefficients, which account for the randomness, but our coefficients don't do that. They're just constant. All right, and that's all. Thank you.
Thank you very much. Looks like we have time for a question or two. So one of the questions I will ask is, you talked about the methods of approximating the differential equation. And one of the challenges, of course, is wondering not just how good is the approximation, but over what time period do we expect it to be reasonable? I know in classical mechanics, the orbits of planets, this is one of the great challenges. And there are difficulties in determining exactly where Pluto will be at any time in the future, but we can at least prove some kind of boundedness results, that Pluto will be somewhere in this band. Is it possible to do some kind of upper and lower bounds as you do the Runge-Kutta and other approximations to say, well, look, we don't know exactly where we're going to be, but we have this confidence window as we go forward in time. And of course, as you go very far forward in time, the confidence window is probably going to get to the point where 115 people, 115% or less will be dead, so it may not be useful. But any thoughts about something like that?
Yes, there are confidence intervals on Euler's method and Runge-Kutta. And of course, this one is fourth order, but you can go arbitrarily high in order and it will get tighter and tighter the more terms you consider. The numbers are out there. I don't remember how accurate Euler's method or fourth order Runge-Kutta are.
It just, one of the real challenges is when we're trying to estimate, for instance, how long we have a lockdown, trying to get a sense of how effective will this be. Are we talking about something on the order of a month or to some extent, 8 months? So
Yeah, those are
you.
definitely. Yeah.
Any other questions? All right, if not, have as happy of a Thanksgiving as you can, and we will resume class on Monday. Have a good one, all.